Welcome back, everyone, to the online Graphs and Matroids seminar. Today, we're happy to have Ruth Luo from University of South Carolina. Ruth, whenever you're ready.
Okay, yeah, thank you so much for the invitation, and thanks for listening. So I'm going to talk about some extremal problems for graphs and hypergraphs. There's no matroids here, so I'm sorry about that, but I hope you can still find something interesting here. So all of this work is joint with Alexandra Kostochka and Grace McCourt. So I'm going to talk about Dirac's theorem. And most famously, this theorem is about Hamiltonian cycles. So Hamiltonian cycle in a graph G is a cycle that visits every vertex of G. And the first type of extremal result about Hamiltonian cycles was due to Dirac. He proved that if a graph has minimum degree at least n over 2, then it has a Hamiltonian cycle. So this paper from 1952 was a very influential paper, but for some reason slightly difficult to find. But in this paper, not only did he prove this result, he proved another result that I'll show on the next page for graphs with some some bounded circumference. And then in this paper, he also introduced k-critical graphs. So a very nice paper, somewhat hard to read though. Okay, so here are some other results which were buried inside his paper. Every graph with minimum degree k, which is at least 2, contains a cycle of length at least k plus 1. So to prove this, you can prove it greedily. You just have some longest path. Look at the endpoints. The endpoints must have all of their neighbors inside of the path. So there must be some cycle of length at least k plus 1. And this is sharp. For extremal examples, we can take a copy of the graph KK, and we have many copies of this, sharing one vertex here in the middle. So here we have minimum degree k minus 1, but the longest cycle has length k. So this is best possible. And well, here we have a cut vertex. So we say a graph is 2 connected if the removal of any vertex does not disconnect the graph. So in other words, it doesn't have any cut vertices. So Dirac proved that then if we require a graph to be 2 connected, so we get rid of this previous bad example, then in fact, we can do much better than a cycle of length at least k plus 1. We can guarantee one of length at least 2 times k, or in the case where k is very large, we can find a Hamiltonian cycle. So this is the main result that we're going to focus on today. And moreover, this is best possible because for construction, I can take almost the same construction, except now I have a bunch of cliques that share exactly 2 vertices. So these are cliques of size k. And you can show here that the longest cycle contains only 2 of these cliques. So it'll have length 2k minus 2. And as another extremal example, we have this complete bipartite graph. One side has size k minus 1, the other one has all of the other vertices. But here the longest cycle again is 2 times k minus 1. And moreover, whenever we have large number of vertices, this complete bipartite example, not only is it 2 connected, but it's going to be 3 connected, 4 connected, all the way up to k minus 1 connected. So in this sense, we cannot improve this theorem by requiring higher connectivity. This is where it sort of remains. Okay, so just to motivate the result for hypergraphs that we're going to talk about, I'm going to give an idea of the proof of Dirac's theorem. So for that, he used a notion which is not so common of aligned paths. So let's say we have 2 paths P and Q. We say Q is aligned with P. If every time they share some vertices, the vertices appear in the same relative order. So if U comes before V and Q, then it also comes before V and P. So here, this is an example of 2 aligned paths. On the other hand, on the next graph, these 2 paths are not aligned. Okay. So with that in mind, Whitney's theorem for 2 connected graphs this is like a two-connected version of Menger's theorem, says that if we have a two graph, there exists two internally disjoint XY paths for every pair X and Y. So Dirac proved a strengthening of this with almost the same proof. So again, we have a two-connected graph, but now we fix some path P. So the enemy chooses the path P, and then his result says that there exists two internally disjoint XY paths, which are both aligned with the path P that we're given. Okay, so he's going to use this theorem in his proof. But actually, there's a slight modification that we can use to shorten the proof of Dirac's theorem. Okay, so still the same setup. We have two connected graph, and we fix some XY path P. So here's our path. And then we now fix any other vertex Z, which can lie on the path or it can be somewhere outside. So what the new lemma says is that there exists two paths, P1 and P2, such that P1 goes from X to Z, P2 goes from X to Y. These are internally disjoint and they're both aligned with P. And the idea behind this proof is pretty simple. We're going to induct on the length of the path P. So let's say we have this underlying path P, and then if we're doing induction, then we can look at the subpath starting at the second vertex going to the end. And then I find these two paths, P1 and P2. So what I would like to do then is to extend these paths to become paths starting at X instead of the second vertex. So I'm going to then use the property of two connectedness. When I delete the second vertex here, I'm able to find a path starting from X to one of these three paths here, P1, P2, or the rest of P. And then we just consider cases. If this path first hits, say, this red path here, then now we can just combine these paths like this. And for the other path, I just add this edge here from the first to the second vertex of P. And then another case, so when this path from X touches first the original path P, then what I'm going to do is follow this, walk forward until I touch either the red or the blue path, and then follow the rest of that path. Okay, and then here are the new paths I get, or again, I add this first edge to one of the paths. Okay, so with this lemma, we can now prove Dirac's theorem. So typically, if you see this proof of Dirac's theorem for Hamiltonian graphs, you might see like it's like a corollary of theorem, and you see some sort of formation where you have some cycle, and then using pigeonhole principle, you can show you have some edges like this, and then you take this cycle here. Okay, so this was not the original proof of Dirac's theorem. Instead, it used something called a lollipop. So a lollipop is some cycle, C, and some path, which intersects the cycle at exactly one vertex, which is the endpoint. So we're going to choose an optimal lollipop in the sense that we first maximize the size of the cycle and then maximize the size of the path subject to that. Okay, so here's maybe an example. And for the sake of contradiction, we'll assume that the cycle is not long enough. So we have a cycle of length less than 2K. So some observations, if I look at this last vertex in the path, then, well, the first observation for any vertex actually is that it cannot have two consecutive neighbors inside of the cycle. Otherwise, we can just add this inside the cycle, get something longer. And another observation is that if this path has length L, then we're not allowed to be neighbors with any of these L closest neighbors or L closest vertices in the cycle. Otherwise, I can extend this by including the entire path somewhere here and then going around. This gives us a longer cycle. So then if we're counting then the number of neighbors that C can have, well, it could be adjacent possibly to everything in P. We can't do anything there. But inside the cycle, I have here, I'm throwing out 2L vertices. And for the rest of the cycle, I can get at most every other vertex. So here, the bound I get, I can cancel out these L's. And then I have this C minus 1 over 2. I assume that C was less than 2K. So this is less than K. All right, so this is a contradiction here because we assume we have minimum degree at least K. And so in the case where we're trying to prove that when K is equal to N, that we have a Hamiltonian cycle, or N minus 1 over 2, then we already finished the results. But for smaller K, there's one last step, which is going to use these aligned paths. So here's our lollipop. And what we showed then is that all of the K neighbors of UL plus 1 must be somewhere in this path here. And now I'm going to choose some path P, which is this highlighted path on the outside. I start with this vertex X, this vertex Y, and for my special vertex Z, I'm going to let it be the first neighbor of Y inside of this path. So this lemma that we proved then says that we have a pair of aligned paths, one of them going from X to Z, the other one going from X to Y. And in particular, for this path going from X to Z, because it's aligned, when we hit Z, we have not visited any of the vertices on this side of the path. So that's going to be very useful for us. We're going to trim these paths so that they each intersect the cycle at one vertex. And then the blue path is going to intersect the segment from Z to Y in one vertex as well. So we get something like this. And now these are genuinely disjoint paths. Okay. So now we claim that we can find a cycle which contains the last vertex Y, as well as all of its neighbors. So let me draw the path, the cycle. So I take this path, I go all the way to Y, and then I go to the neighbor of Y that appears as close to this endpoint as possible. Okay, then I go to Z, go around this red segment. And then to complete the cycle, I have two choices of how I can travel along C. So I go along the longer segment. Okay, so when I choose this segment inside C, I'm going to choose one that I throw away at most half the number of vertices in the cycle. So in particular, this gives us a new cycle whose length is going to be, so C minus half of C, at least. And then now we have K neighbors of Y plus 1 for Y itself. And then we maybe subtract 1 for Y because it could be the case that one of these neighbors is inside the cycle, just one of them. Okay, and so then this gives us a longer cycle. This is a contradiction because we assumed that the length of C was less than 2K. So this was the idea of Dirac's theorem, and I wanted to include it because it's going to sort of inform how we prove the result for hypergraphs. But before we talk about the hypergraphs, just some more musings about this. So we had this lemma that if G is 2 connected, then if you give me any XY paths, I can find 2 internally disjoint XY paths which are aligned with it. So one question would be, does this generalize to higher connectivity? So for instance, if it's 3 connected, can I find 3 aligned paths? And unfortunately, there are some bad examples. So here I can build a graph which has very large connectivity, but I'm still not able to find even 3 aligned paths. So here I have some ginormous complete graph, and then I'm going to, I have like my vertices here in A, vertices in B, inside the clique, and I assign 2 new vertices, X and Y, such that X is adjacent to all vertices in A and only one vertex of B, and similar for Y. So the path here, which I have drawn in red, has all of the vertices in B appearing before all of the vertices in A. So if we want to find some aligned paths, they must also have the B vertices before the A vertices. So let's see how many we can do. Well, I can use this edge one time. Maybe I go something like this. Similarly, I can use this edge only once. Maybe I have a path like this. And now I'm stuck because to go from X to Y, I have to go through A and then I have to go through B. So these vertices will appear in the wrong order. Okay, so again, this does not depend on the connectivity because I can bump this up even more and still have the same issues, even trying to find 3 aligned paths. So here's just a general question, which is not very well defined, but if you're interested, you can think of it. So given a k-connected graph G and an xy path P, under what conditions can we guarantee L internally disjoint xy paths aligned with P? So maybe you need some condition on, say, like the minimum degree as well. Okay. But with that said, I want to now talk about hypergraphs. So hypergraph H is going to be a set of vertices and a set of edges, and each edge is some subset of the vertex set. So this is a generalization of the graph. And in particular, if we have that every edge is the same size, say R, then we will call the hypergraph R uniform. So from now on, every time I say R, this is referring to the uniformity of the graph. Okay, so the degree of the vertex in H is going to be the number of edges containing that vertex. And we use this delta of H to denote the minimum degree over all vertices in H. So we want to prove some Dirac type results for hypergraphs, which are of the sense we have some minimum degree, which implies the existence of some long cycle. For that, we should first define what it means to have a cycle in a hypergraph. So there are a couple definitions, but the one that we're going to use is that of a bearish cycle. So this is a bearish cycle of length L. We have L distinct hyperedges, L distinct vertices, such that the ith vertex and the i+1th vertex are contained together in the ith edge. And of course, each of these edges, other than those 2 vertices, will contain many other ones, but we have sort of this special set of representative vertices here. So in this picture, we have an example of a 4 cycle, which is a graph, and then 2 different bearish C4s. And there's many other ways that I can draw them as well. So this is a family of hypergraphs, not just a single one. And for simplicity, so we can write the bearish cycle as an alternating sequence of distinct vertices and distinct edges, where if I look at some edge, it's going to be containing the 2 vertices around it. So our goal is going to be to prove these similar results for hypergraphs, and it will help us if we can apply as many results from graph theory for hypergraphs as we can, just because it's easier to prove things for graphs. So for that, I want some sort of bijection between graph and the hypergraph. The one that we'll look at is called the incidence bipartite graph. So given a hypergraph H, I construct this incidence bigraph by giving every vertex in H a vertex in the incidence bipartite graph, but also giving every edge in the hypergraph its own vertex. So this gives me a bipartition into the vertices and the edges of the hypergraph. And then I place the edges as expected. I place an edge between X and Y if the corresponding vertex X is contained in the edge Y in the hypergraph. Okay, so here's a picture of an edge. It contains here 5 vertices. I give it its own vertex over here. And then I make it adjacent to, oh, sorry, did I freeze just now?
Just for a second. If you're drawing things now, I can't see. Oh, there we go.
Yeah. So I saw it wasn't on the computer showing up either. Okay. So we construct this incidence bipartite graph, and as an example here, I have some edge. It has 5 vertices. I give it its own vertex, and I make it adjacent to every vertex it contains. So I do this for all of the hyperedges, and then I get this bipartite graph. And in particular, it has some really nice properties. Oh, 1 second. Okay. So the properties, if I have an R uniform hypergraph, then every vertex corresponding to an edge has degree R. And moreover, if I have some minimum degree condition in my hypergraph, then all of the vertices corresponding to the actual vertices will have degree at least delta of H. And most importantly here, if I have some bearish cycle, so this is an alternating sequence of vertices and edges, if we have a bearish cycle of length L, this is going to give us a cycle of length 2 times L in the hypergraph, in the incidence bipartite graph, and vice versa. So this gives us a nice way to relate these 2 different objects. Okay, so there are a series of different Dirac type results for cycles and hypergraphs. I mentioned only a couple here. So for these, I'm going to let H be an n vertex R uniform hypergraph, minimum degree delta. So Coulson and Perono was the first sharp result for guaranteeing a Hamiltonian bearish cycle. So if we have minimum degree at least this, we can find such a bearish cycle. But namely, this works only when R is small compared to n. So here we have R is little o of the square root of n. And the reason we get this is because they use some sort of probabilistic argument, which is some modified version of Lová's local lemma. And this is what they needed for the calculations to go through. Okay, and also they proved this more in a general. They didn't just prove it for hypergraphs. What they were doing was they take some normal graph with minimum degree at least n over 2, and then you're going to color the edges so that no color is used too many times. And then from that, you will find a rainbow Hamiltonian cycle in the graph. So you can relate these two because what you can do is you can color the edges in a graph according to which hyperedge they are. So give every vertex or every pair of vertices in some fixed edge the same color and a different color for each hyperedge. And it's not hard to see that a rainbow Hamiltonian cycle in a graph is equivalent to having a bearish Hamiltonian cycle. Okay, so this was a really impressive result. And then we were able to extend this by just bringing down the conditions that we need for R. So we have here now sharp results for all combinations of R and N. So in particular, when R is at most roughly N over 2, then we get the same bound here as the previous result. But when R is large, at least N over 2, then we get a much more modest bound for the minimum degree. We just have that it needs to be at least R. So here the hypergraphs are going to look a little bit strange because now the uniformity is at least N over 2, which means every edge contains almost half or at least half the number of vertices. So these are sharp, and here are some extremal examples. For small r, I'm going to take cliques of order n plus 1 over 2, sharing a single vertex. And for big R, what we're going to do is we take R uniform, R regular hypergraph, whichever one you want. And by hand-checking lemma, you can check that this will have exactly n edges. So if we remove a single edge from them, we now have n minus 1 edges. This is just not enough edges to give us a Hamiltonian bearish cycle. Okay, so in this case, actually, for the big R, there's sort of a phenomenon going on here where as the sizes of the edges grow and grow and grow, it becomes easier to find these forbidden bearish objects. Okay, but that's for Hamiltonian cycles. Now let's talk about if I just want to find a bearish cycle of length at least k. So actually, there's this quite old result by Bermond, Jeremy Heinemann, and Soto. Hope I pronounced that okay. where they proved this minimum degree here. And then we were able to improve this in the same paper. Basically, we just reduced the plus r minus 1 term to plus 1. And we can find a bare cycle of length at least k. So the examples are not too surprising. We basically just have hypergraph versions of whatever the extremal examples we had for Dirac's theorem originally. So here we can just take a bunch of cliques which share some cut vertex. And so, okay, we didn't define a cut vertex here for hypergraphs, but hopefully it's clear what it means. And for similar reasons here, I cannot find a cycle of length greater than k. So then the question is now, similar to the graph case, can we do better by requiring two connectedness? And for this, the answer is also yes. But let's first talk about what it means to be a two-connected hypergraph. So, okay, we could maybe define it as it doesn't have any cut vertices, but what does that mean? So actually the notion of two-connected that we will use is that the hypergraph is two-connected if and only if I look at the incidence bipartite graph, which is a graph, and this is two-connected. So in particular, if this is two-connected, then the incidence bipartite graph, it has no cut vertex in y. So y is corresponding to the edges of the hypergraph. That means if I delete any edge, I don't disconnect the hypergraph. But also, we don't have any cut vertices in x, where x is corresponding to a vertex in h. But whenever we delete a vertex in the incidence bipartite graph, it doesn't just correspond to deleting the vertex in the hypergraph. What it is we delete the vertex, but we also now remove it from any of the edges that contained it rather. So those go from r edges to r minus 1 edges. And if doing this property does not disconnect the graph, as well as the first property, then we say it's two connected. Okay, so it's a little bit annoying that we have this definition, but it is necessary because in graphs, well, if we have a cut edge in a graph, then we also have a cut vertex because we can just delete any vertex incident to that edge. It'll also delete the edge. But in general, it's not true for hyperedges. So here I have this cut edge, but if I now delete any vertex here and just shrink down the edge, I still have a connected hypergraph. Okay, so these are not the same things when we move even to 3 uniform. Okay, so then here is our results. So this is just the old result that we had for graphs. If we have minimum degree k, then we have a cycle of length k plus 1. And this is what I showed previously, a hypergraph version of this result. But now let's see the two connected version. This was Dirac's theorem for graphs. And so what we prove then is if we have the same minimum degree as we had here, this was the minimum degree that we needed to get a cycle of length k plus 1. If we up the connectivity, we get a two connected graph, we have the same minimum degree, then now we can find a bare cycle of length 2k. So we already solved the case for Hamiltonian, so we can just assume that this minimum is equal to 2k. Okay, so this is the new result. We put it out earlier this year. And in particular now, if I don't care about if I'm not just looking at the minimum degree now, if I say I just want some bare cycle of length at least L, okay, then I can plug in L into these equations here. Without any conditions on the connectivity, I need a minimum degree of L minus 1, choose R minus 1 plus 1. Whereas over here, I need something only like L over 2, choose R minus 1. So in particular, then the minimum degree required is smaller here by roughly a factor of 1 over 2 to the R minus 1. So this is pretty significantly better, especially when R is large. Right, if anyone has any question, feel free to stop me. This is just the same result repeated. And here are the extremal examples, which again are just basically hypergraph versions of the extremal examples for graphs. The first one is going to be many cliques of order k, sharing exactly 2 common vertices. And the second example is going to be a version of the complete bipartite graph. So here we have a set of size k minus 1, and then I put all of the other vertices in a set. And the edges are going to be every edge which contains at most 1 vertex in the larger set. So in terms of finding some bearish cycle, the best that we can do is just go back and forth between these, because I cannot have 2 consecutive vertices. I cannot have 2 consecutive vertices inside of the larger set. So here again, my largest bearish cycle is going to have length less than 2k. And similarly, this is a very connected hypergraph. So this result cannot be further improved by requiring 3 connectedness or 4 connectedness, so on. Really, this is the best possible. Okay, yeah, so you can check that each of those have the minimum degree 1 less than what we have here. Okay, so I'm going to then give the proof idea. So a lot of the details I showed in a more viewer-friendly version for the proof of Dirac's. So we're going to use those ideas, but of course there has to be some special extra steps because we're now working in hypergraphs instead of graphs. So let's let H be an R uniform and vertex 2 connected hypergraph. And we can observe then, if we look at the incidence bipartite graph, and I have some path from x to x, where x is representing the vertices, then this corresponds to a bearish path in H. Okay, so I didn't define bearish path, but it's defined similar to cycles, exactly how you would expect it. Okay, and so why is this true if here's my path starting from x to x? Well, each of these vertices over here represents a hyperedge, so this is my bearish path. And similarly, now if I have some path from y to x, where y was representing the edges in the hypergraph, this is almost a bearish path, but it begins with an edge instead of a vertex. So we call such things partial bearish paths, and similar from y to y. So where we're going to be able to use this is, well, if we're working in just graphs, and if I have a 2 connected graph, then if I fix any subset and some vertex outside here, then I can find 2 internally disjoint paths from that vertex into the subset over here. So here then, if I want to now look at what this means in hypergraphs, I have some set here, then I can find either bearish paths or partial bearish paths into this set, something like this. And that's going to be really useful for us. Okay, so the proof idea starts very similar to the lollipop proof of Dirac. Here we're going to now take bearish lollipops. So we have some bearish cycle C, bearish path P, connected at 1 vertex. And we're going to first choose C to be as long as possible without loss of generality. Or for the sake of contradiction, we assume that the length of C is less than 2k. And then subject to this, we choose P to be as long as possible, where if X is the endpoint of P, then the last condition is that we're going to choose our combination of C and of P so that as many edges in the bearish cycle contains X as possible. So in the actual paper, we had 1 or 2 more criteria that we used, but for the sake of this demonstration, I think these 3 are simple enough. Okay, so here's our lollipop, which in actuality looks something like this, but this is pretty messy. So in the next pictures, I'm just going to draw it like this, where here I can view this as like the projection of these edges. And I'm assuming that each of the edges in this picture are distinct edges, hyperedges. Okay. So now after I choose my lollipop, I can define H prime to essentially be the rest of the hypergraph. So every edge which was not used in either the cycle or the path part of the lollipop. And if I have a vertex V and a vertex X, we say that they are H prime neighbors if there exists an edge in H prime, which contains the two of them. So some edge which is unused by the lollipop. And our goal is going to be to use those edges to get some contradiction by showing that we can find either a longer cycle or a longer Burge cycle or a longer Burge path. Okay, so here, the first observation, very easy, is that this endpoint here, X, does not have any H prime neighbors outside of the vertex set of the Burge cycle or path. Because if it did, then I can just, extend this path to get something longer. And then very similar to the previous proof we had, we can show that H prime will not have any, X will not have any H prime neighbors inside the cycle, except maybe this vertex here. So why is that the case? So for similar reasons, we cannot have any H prime neighbors in these L closest vertices here, because if we did, we could extend this to some longer Burge cycle. And then one extra case that we need to do. So before we had that just trivially no vertices had two consecutive neighbors inside the cycle. Here we're now looking at H prime neighbors. And if I have some two consecutive H prime neighbors of X inside the Burge cycle, then by definition, for each of them, I have some edge in H prime, which contains that vertex in X. So if those two edges are distinct, then of course I can just expand the cycle as usual. So then we need to consider the case where it's the same edge here. And this is where we use the fact that we choose the lollipop so that it contains as many edges which contain X as possible. So in particular, if I look at this edge in the Burge cycle, if this doesn't contain X, then I can replace it with this H prime edge that does. And then if it does contain X, then I can now take this edge and then go back using the H prime edge and get so using the same arguments as before, we have that the number of H prime neighbors is going to be strictly less than K. But that's not going to be the degree. This is just the number of H prime neighbors. So to get a count on the degree of X, every H prime edge contains some R-1 other vertices. And each of these R-1 vertices are going to be H prime neighbors of X. So here we can just bound it by the size of the neighborhood, choose R-1. So that's the number of edges outside containing X. We also need to count the number of edges inside the Burge cycle and path that contain X as well. So here we have this quantity here. This term is going to be at most linear. Okay, so here we already get a pretty good bound, but of course we would like a sharp bound as well. So first, just a little preview on the next slide. How do we handle this term here? We can handle it by considering, okay, so what happens if we are contained in some edge of the cycle? So maybe something like this. We have this edge EI, which contains it. Well, then what we have is that neither of those vertices incident to this edge can be H prime neighbors with X. Otherwise, then we can just extend this cycle. So in other words, every time I have some edge in the cycle which contains X, it's going to then kick out two possible H prime neighbors of X. And in particular, then if we increase this, we need to decrease this term here. And this term here is going to be decreasing at least quadratically because I have this binomial coefficient. Okay, so basically in the extremal examples which we analyze, we can assume that the number of edges in the cycle containing X is as small as possible. Okay, and then the last part of the proof is just using this idea where I now have the aligned paths. So here is my lollipop. Again, I take this path here, and then I'm looking at all of the H prime neighbors of X inside of the path, where each of these edges actually probably looks something like this, but for simplicity, I draw it like this. So I apply this lemma, but what I'm doing is I'm applying it to the incidence bipartite graph. This is going to give us some paths, and the paths in the incidence bipartite graph will give us some bearish paths or bearish partial paths in the hypergraph. So here I have some aligned bearish path from V1 to X. Here I have another one from V1 to Z. And so similar to before, I can now trim these down, so they intersect at only the points I want once. And okay, so here, this could also have been an edge, not a vertex, so something like this. Okay, and then now, similar to the idea we had for the graph case, we can find this bearish path, which now contains all k, or at least k H prime neighbors of X as well as X here. And then we'll show that this is longer than the length of the bearish cycle we started with. Okay, so that's the idea of the proof. There's a lot of details which are kind of skipped, but hopefully that's okay. So one quick application here, which follows pretty naturally. So we say a graph has codiameter k. If between every pair of vertices, I can find a path of length at least k. And equivalently, so if I have a pair of vertices x and y, then g plus xy will have some cycle of length at least k plus 1 containing the specified edge xy. So here, it's not hard to show that the minimum degree at least k is going to give us codiameter at least k. And this is best possible, again, by taking two copies of cliques of size k, sharing exactly, many copies sharing exactly two common vertices. So if I want a path between those two vertices, I can only go in one clique here. And here I say two connected, which does not really seem like it should have anything to do with this problem, but indeed it's necessary here in order to get any sort of interesting results. Because if I take two cliques of size n/2, joined by an edge here, then I have very large minimum degree. But for these two vertices connecting the edge, the longest path between them is length 1. Okay. So there are some extremal results here concerning codiameter, which I won't get too much into. But as a corollary of our result, we get that the same minimum degree condition gives us codiameter at least k. So we have a bearish path of lengths at least k between every pair of vertices. The proof is very simple. So with this minimum degree condition, I can find a cycle of length at least k. And now I'm going to look at where my vertices x and y lie relative to the cycle. So if they're both inside of the cycle, bearish cycle, then I just take some segment which contains at least half the number of edges. So at least k edges, that's good. So the next case is when one of the vertices is outside, one is inside the cycle. But then here we can just use the property of two connectedness or even connectedness, find some path or partial path from this vertex x into the cycle, and then extend it to y, taking a longer segment. And then similar if they're both outside. Okay, so pretty naturally we get this result for codiameter as well. Now for the last few minutes, I just want to talk about some open questions. This one's a pretty tough one. So in graphs, we have this Dirac's theorem, and not much harder to prove is something called Orr's theorem, So Orr's theorem says now, instead of having just some global minimum degree condition, if I have for every pair of vertices x and y, that their degree sum is at least n, if they're non-adjacent, then it's Hamiltonian. So this is going to imply the Dirac's theorem. But what I would be interested in, and what I'm sort of working on now, is some sort of Orr's theorem for hypergraphs. Does there exist a function f in terms of n and r, such that if for every pair of non-adjacent vertices in a hypergraph, our uniform hypergraph, if their degree sum is at least this quantity, then the hypergraph must be Hamiltonian. So the answer, well, maybe there does exist such a function, but if there does exist a function, it needs to be very large. So here I have this bound n-2, choose r-1 plus 2, because I can take, for example, a clique of order n-1, and then I have some vertex out here, I put it in one edge. So this does not have a Hamiltonian Bearish cycle because I need every vertex to have degree at least 2. But here you can check that the degree sum is very large. And in particular, this is not super meaningful because, well, if I have just a vertex, the maximum degree I can have in R uniform is like n-1, choose r-1. Okay, so this is quite a lot. But in particular, it's not very useful to prove a result like this other than for the sake of proving it, because this is not going to give us, as a corollary, the original Dirac's theorem for hypergraphs. So what I showed earlier is this version of Dirac's theorem where I'm looking for Hamiltonian Bearish cycles. The bound we need is like this n-1/2, choose r-1. So this quantity is smaller than what we have here by roughly like 1/2 to the r-1 again. Okay, and that's just because we have this binomial coefficient, which is growing very large. Okay. So as another attempt, if you wanted to prove some sort of Orr's theorem, what you could try to do is, instead of looking at just the degrees in terms of the number of vertices, maybe you look at the size of the neighborhoods. So the number of vertices that each vertex is adjacent to. This is equivalent to like the number of, or the degree in the two shadow, if you're familiar with that terminology. So here I just define this as this d prime of v. It's going to be the set of vertices for which the co-degree of u and v is at least 1. So they're contained in at least one edge. And then we can ask the same question here. Does there exist some function such that if the sum of these new degrees is at least that function, then this implies that the graph must be Hamiltonian. And so still, unfortunately, the answer is no for general R, because I can construct for large R, say like linear, in N. Some bad example, consider say your favorite clique of size S, and we're going to then blow it up. So here, every vertex I turn into n/s vertices, and the edges are just these giant edges here. Okay, so here I have only S choose 2 edges, where if S is small compared to N, then this is certainly not going to be enough to form a Hamiltonian Bearish cycle. But if I'm just checking the neighborhoods of each vertex, actually every vertex is adjacent to every other vertex in a sense. So here, this is sort of maximized as much as it can be, but I still cannot find Hamiltonian Bearish cycle. So the challenge really is, I mean, it's a hard problem, but you should think carefully of how we're going to define this problem that we're looking at. So I think maybe when R is small, it makes sense to do something like this. When R is large, maybe it makes sense to do the previous definition of degree. Or maybe you do something even more different using like co-degrees or something like that. Okay. And okay, just a couple more. So some more open problems, which I think are more feasible. You can just take whatever problems you have for graphs, long cycles and graphs, and try to prove them for hypergraphs. So here's one of my favorite problems about Hamiltonian cycles, which is very simple to prove. you take a linear forest now. Linear forest is a forest where every component is a path. And if we have L edges in this linear forest, then Poe should prove that this minimum degree condition is going to guarantee you a Hamiltonian cycle which passes through the linear forest. So this is sort of like a strengthening of this codiameter thing where we have some edge and we want to include it in some long cycle. Okay, so here we can then ask for some sort of version for hypergraphs. And I just want to give a couple options here. So, well, okay, I have my linear forest, and then I want to complete it to a cycle, bearish cycle. One way you can do it is that the enemy chooses the bearish linear forest, and we want to complete it to a Hamiltonian bearish cycle. So the difference here for the hypergraph is that this edge may contain many different vertices. So in particular, I cannot use this edge somewhere in the bearish cycle over here. So there's a challenge here where I'm both choosing the vertices and also the edges to throw out. And another variant, which would be easier, would be to just ignore the edges of the bearish linear forest. So if I delete these edges, what this is now I've partitioned the vertices into some set of disjoint paths. And then here I can ask the same question. Just find these disjoint bearish paths connecting the specified vertices. Okay, so these are some nice problems, I think, to consider, which would not, at least the second one probably is not too hard. Okay, but I will stop there. Thank you.
Okay, so on the count of three, let's unmute and give Ruth a round of applause. 3, 2, 1.
Thank you.
Okay, and are there any questions?
Okay, I had a question.
Mm-hmm.
All these results are for R uniform.
Yeah.
What if I said that all of the edges had R or R+1 vertices, for example?
So some lower bound on the size of.
Well, maybe not just a lower bound, but yeah, the lower bound would be one way of approaching it. The other one would be to say, okay, they can be within some sort of interval.
Yeah.
And I don't know how heavily dependent on it being R that you are.
So our proofs did depend on it because there were some parts of the proof where we get a contradiction because we say like this edge must contain a bunch of vertices, too many of them. So in that case, I think maybe R+1 might work if we have R and R+1, but I think anything bigger than that, probably not. Yeah.
Yeah, that was kind of what I thought might happen.
Yeah, so we also had earlier, like a few years ago, I proved with Zoltan Ferretti and Alexander Kostochka a version of Dirac's theorem for completely non-uniform. So the edges can be anything from like 0 to n. And we have sharp results there. The proof was a lot easier. It's just like the minimum degree condition is really large. It's like exponential, like 2 to the n over 2 or something like that.
Okay.
Mm.
Thank you.
Yep.
Other questions? Maybe I can ask one. So you're explaining how it's kind of hard to even come up with a good extension of Orr's theorem because it's hard to say what degree condition you want. I'm wondering if a similar thing happened with your definition of two connectivity for hypergraphs. Like, are there other natural definitions of connectivity for?
So some of them would be stronger. So for instance, like in graphs, if it's too connected, if you delete a vertex, delete all of the edges containing it, and it's still connected. So if that's the case here, I think that would just be like a strict subset of what we define as too connected. Yeah, I'm not aware of any other popular notions of two connectivity though.
Any other questions?
The terminology lollipop, Was that the terminology that Dirac used?
I believe so, yeah.
And is that sort of standard in graph theory?
So the not issue, but the fact is that Dirac's proof is not like the standard proof of his theorem. The standard proof is due to aura. So I think this lollipop thing is a little bit like underground in that sense. But yeah, I had not heard of it before I looked up this paper.
Okay, I call these things tadpoles, but I didn't know about lollipops. So
Yeah, that's a good name too.
Okay, maybe I'll stop the recording and we can continue the discussion off the air.